Hello and welcome everyone to the third and final online session of SAT organized by SEDS Sri Lanka in collaboration with SEDS SLTC. We are absolutely thrilled to have you join us today as we launch into this exciting series. To help us make this event a reality, I would like to warmly introduce our official resource partner, Radio Society of Sri Lanka, and our venue partner, Sri Lanka Technology Campus. I am Dinush Pereira, representing the Computing Committee of the Media Unit of SLTC and the Organizing Committee of SATvision. I will be your moderator for today's session. Before we start today's session, I would like to make a special announcement. The winner from the quiz hosted by the Radio Society of Sri Lanka, Sasmita Kaushan from Bandaranaike College, will be given a free boarding pass for the physical workshop session. Congratulations, Sasmita Kaushan. Now, I would like to invite our Vice Chairperson, Ms. Dilochini Senanayake, to deliver the welcome address.
Good evening. As the Vice Chairperson of SEDS SLTC, I am incredibly excited to welcome you all today. First, a very warm welcome to our guest speaker, Ms. Dilanka, Department Head of Telecommunication Engineering at SLTC and Lecturer Higher Grade. Thank you, Ms. Dilanka, for being here to inspire us today. I also want to officially welcome the powerful collaboration between SEDS SLTC and SEDS Sri Lanka. Together, we are opening up amazing new doors for student innovation and space exploration. A special welcome goes out to our official resource partner, the Radio Society of Sri Lanka. Thank you for partnering with us. Your expertise is going to help our students turn big ideas into reality. To all our members and participants, make the most of this incredible platform today. Learn from experts, network, and let's inspire each other. Thank you and welcome to the event.
Thank you, Dilochini. Now, it is my absolute honor to introduce our esteemed guest speaker for today's session. Joining us is Ms. Dilanka Silva. Ms. Dilanka is the Department Head, Telecommunications Engineering, and is a lecturer, higher grade, specializing in electronics and telecommunication. Ms. Dilanka, the stage is yours.
Good evening to all of you, and I hope you can hear me. So let me share my screen first. Right, I believe you can hear me clearly as well as you can see my screen. So good evening to all of you who have joined this session, and I would like to thank the organizing committee for inviting me for this session. I believe it is a privilege for me as well to share my knowledge with you in this area. So I think you have gone through a couple of sessions prior to this. So I thought that I will be covering some area which might have not touched as of now. But maybe some of you, since you are already in this specific area working on different researchers on satellite, you might know how much the security when we are transmitting information is important. Whereas some of you might not exactly know how much this is really important. So that is why I thought that maybe starting from the basics, starting from the applications, then I will talk about why for different applications this security is really important. And then I will take you through to the different techniques that we use to secure our communication. So let me take you through. So as I mentioned, I believe all of you who have joined today know what is satellite communication and how does it work, what are the frequency ranges. But still, since there might be students who have joined recently who might not have exact idea of what exactly this technology and what is the what exactly we can do with this, because this satellite communication is really, I could say, a very powerful technique, even though here in Sri Lanka, we do not have much of experience nowadays. But this is widely used technique. So that is why I just thought to start with a very quick introduction onto the satellite communication, just to clear that all of us are having the same understanding when I use certain words when it comes to the latter part of the presentation. So I think all of you are familiar with these wordings that you could see, that it is the ground station. When we are talking about the satellite communication, the satellite or the transponder is exactly the equipment which is actually moving or else depending on how it is implemented, which is actually making it possible for the two or more ground stations to have communication together. So when we talk about this communication link, it is really important for us to understand what exactly this uplink, the downlink means, because you will see that when we are talking about different communication networks, different technologies, this uplink downlink is basically something very virtual. That means we are logically defining this uplink and downlink, whereas the physical channel is this air media, right? So in that case, generally, we denote the uplink to be the link that we transmit from the ground station to the transponder, or what we call as the satellite, or else, and the downlink is where we send the information from the transponder to the ground station, right? So why this is important, you will see, is that when we talk about different applications, which I will discuss in the next slide, we can see that some satellite networks in which different applications are implemented will have both uplink and downlink in the same link, right? So in that case, you need to be very clear about it. And I believe all of you know what are the general frequency bands. So we know that generally the satellites are operating in these gigahertz range, whereas some weather stations related satellites will be working on lower frequencies. Whereas here, as you can see, I have listed a few key applications that in which we use this satellite communication. Maybe sometimes you wouldn't have experienced or you wouldn't have known that for these specific applications, we are using this. So rather than explaining here, I would go to the next slide just to show you how the satellite networks power our real world applications, right? Because maybe when, as a user, as an end user, let's say I'm making a voice call, maybe I'm checking what is happening in weather, is it going to rain? And on the other side, when I'm going for some, let's say I'm going for in a journey, so I need to know where I am. That means it is navigation, and also we might be watching TV, right? So in these cases, have you ever wondered that satellites can be the link in between for these sort of applications? So here you can see I have just given you these 4 areas, right? But as I mentioned, there are many more others like maritime communication and other things as well. But here I have just given 4 areas or 4 applications in which we use the satellite links for this connectivity. Right, so the first application is the IDD calls, international direct dialing calls, basically like the voice calls we generate for the for our friends and family members who are outside the country, right? So in that case, basically, we know that I'm making a call and I know that the other party answers the call and we both are in the communication. But have you ever wondered that our call can go through the satellite links, right? So maybe as of now, as a country in Sri Lanka, we do not have this satellite links for this application. Because now we are using fiber communication for IDD applications. But when it comes to the past, right? So as maybe since we have many of the SLTC students, and I believe the others also who would have visited SLTC, would have seen these satellite earth stations, the dishes which are there at SLTC. So these were basically the links that were used by the SLT in the past, maybe in 1990s, to connect the IDD calls as well as internet, right? So which means even though we generate the call in our operator, right? So maybe I'm making a call from other mobile operator, but it needs to go through to another country. We have to have this kind of a link between the two countries. So in such case, we will have this it is possible for us to have this being implemented using satellite links, right? And on the other side, I believe the second application might be a little bit familiar to you anyway, because I think it was the last session was on this, which is related to the weather data transmission. So in this case, generally, whatever the weather, the images, the radio images that captures are being sent through the satellite links to the stations where this, whatever the processing is done, right? So maybe this is a little bit familiar. And the third application that I just wanted to highlight today was TV broadcaster. So maybe some of you might be using dialogue TV, where you might be having that small dish mounted on your roof. So that is basically satellite communication, right? So in case of a TV broadcaster, they can send, right? So maybe not when it comes to the broadcasters coming from other countries, this is a very easy way of sending information, broadcasting, because maybe we can say the security that we want might be a little bit lesser compared to other applications like voice calls, right? But when you look at these applications, the first two and the third one, I believe you would have noticed by now that these arrows are only in one direction when it comes to the TV broadcasting. So this is the speciality when it comes to different applications, as I mentioned. So when we talk about a voice communication, both the parties in the communication will talk. But we know that when it comes to TV broadcasting, yes, the broadcaster will send the images or the videos through the whatever the link, and we will see it. But we cannot send any feedback to the broadcaster. So that is why we have only one the arrows in one direction to show that the communication or the data flow, information flow only in one direction. So this is where we have this concepts of this bidirectional communication and unidirectional communication. So I believe if you are onto communication, you would know whenever we say that bidirectional, bi means two. So that means both the parties are in communication or are sending information and receiving information. But when it comes to unidirectional communication, it is only going to be one direction, right? And the last application I considered was the navigation. So we know that all of us are nowadays, whenever we need to go somewhere that we exactly do not know, we just search it in Google Maps and just check how we can go. So we get the route. So have you ever wondered how we get it? So we are getting it from the navigation satellites. So they are sending the information to our devices based on which we can actually see where we are going and where we want to go, what is the route, right? And here also, there is no way that we can send our comments or our feedback, because it is basically the signals that we are receiving and processing to identify the direction that we move. given that all these 4 applications, I just wanted to go into depth a little bit on the first and the third application, the IDD calls and the TV broadcasting. So let me just discuss the first application, which is the IDD calls. So here, in the previous slide, if you have noticed, I have just shown that the mobile phone is getting connected to the nearest site, and it shows like it is getting connected to the Earth station. But actually, it is not a direct connection that we have. That is why I just wanted to elaborate here. So for a mobile operator or a telecom operator, they have the core network. So actually, the core network is the main part of a telecom network, where it makes the possibility for the users to get connected to the network and then to use different services, and whenever they are making a call, to get connected to the other parties, right? So the user will have to get connected through the core network, and it is the core network that is getting connected to the satellite gateway, and then it will go through the satellite link and will be received by the other network here also through the core network to the user. So this can be for mobile networks as well as fixed line networks, because irrespective of whether the end user is fixed or mobile, this backbone link can be connected either via satellite or else through fiber, right? So in this case, as I mentioned earlier, we can see now when it comes to a voice call, the signal, let's say the user A on the left-hand side is talking. That means he or she is sending the information. So which means at a particular point, at that point, the information is flowing from this direction towards here. And maybe let's say as a reply, the other person is talking. So the signals will flow the other way. So which means if we take this particular link here, which you can see, it is going to be bidirectional. So the signals can go in this direction as well as on the other direction, right? So which means whatever the points that you tap here in this network, you can get information which is flowing in the network, right? So you will see why I introduced this when we are starting to discuss about security, right? And in addition, as I mentioned, when it comes to a mobile network, if our backbone is getting connected to other countries through satellite, the mobility is not possible only due to the mobility provided by the operator. Obviously, the operator will have to provide the mobility, but on the other side, the satellite link should be stable, right? Because we know that maybe with the movement of the Earth, as well as the movement of the users might change from one place to the other. So maybe the core network component that this user is connected is now changed to another core network component, which is connected to a different satellite link. So which means there should be handovers in the satellite link as well, right? So which means you can see that when we are having this communication or the telecommunication or voice call in mobile networks, it is not only the mobile operator who is responsible for maintaining the service, but it is up to the satellite operator as well, right? And next, coming on to the TV broadcasting. So when it comes to the TV broadcasting, if we look at the different boxes or the components that we have, so whatever the videos or the whatever the content that we need to send will get processed. So I believe all of you know that when it comes to the information, if it is analog, we have to do the analog to digital conversion. And then maybe we might need to do encoding, or what we call the source encoding, which means that we have to represent whatever the symbols or information in a compressed manner, because we want to save the information that is being transmitted through the network. Sending information through a network means a cost. So saving bits or saving information or sending the information with less amount of bits is what we call as efficient. So to make our networks efficient, we need to look at the ways that we can compress our information and send. And also we have to ensure, as I mentioned, our links are reliable. So in order for us to have reliable communication, we use another technique called channel encoding and decoding. So there, what we try to do is to make the bit error rates less in our communication. So all these things are there for whatever the communication system, which is there also for the satellite system as well. So for each and every link, each and every hop that we have, the same concepts will be applied, right? So in the TV broadcasting, it will go to the base, not the base station, but the ground station, the earth station, and then it will go to the transponder. And there are two ways actually that we can have the TV broadcasting. One way is that the local broadcaster can get the information from the satellite, and then they can process it and then distribute it to the viewers. In such case, the end viewers will not have this dish, right? So as an example, let's say the SLT is providing the POTV. So we know that the last mile is fiber, right? But we do not know when we are watching, let's say, a foreign channel, maybe UK, USA, Korean, or whatever channel, the information is coming from a different country. So we exactly do not know whether we are, like, we know that in Sri Lanka, we do not have satellite networks, but if we take in general, it can be through a satellite link as well as it can be through fiber. So in such a case, the broadcaster, the local broadcaster can capture the information and give the information or broadcast it through wired fiber. That is another option, or else as Dialog TV, as in Dialog TV network, the end user will have their own dish. So either way, it is possible. So having this idea about on all these hops, I believe now we need to go on to understand how the security applies into this sort of networks when we have the satellite network specifically, right? So when it comes to an international call, so let's recall back the service of international calls. So let's assume there is somebody who is trying to get into our network or our links or the information that is being transmitted. So at whichever the point that we consider in for a telecommunication network, as soon as somebody outside is getting connected, the users are directly impacted. That means, let's say somebody is trying to capture what is transmitted in my link. So which means they can hear what I'm talking. So when it comes to telecommunication, we know that the voice that we transmit or the data, maybe we are doing some transactions, we are sending username passwords. So that is private information. So privacy is really important when it comes to these kind of applications. So it doesn't matter at which point that somebody is trying to, or somebody is being able to capture the information, the users are going to get impacted directly. So on the other side, if you think about an application like broadcasting, so we know that broadcasting, it is unidirectional. So the content provider will be sending information on the uplink earth station, which will be received by the downlink and viewers will see. So in this case, think what is going to happen if somebody, an attacker, is trying to capture or get into this link. What they can do. So here they can, yes, view the videos, view the broadcasting live stream that happens, whereas they can also inject or replace the content, right? So which means that is going to impact the viewers, right? So it is going to impact the broadcaster and the users as well. That means the whole network is impacted. So whatever the content that the attacker is injecting to the network will be transmitted to the users. So this is critical, right? So I will show you some examples where in the history this has happened. But what would happen if somebody has intercepted at the receiving or the downlink Earth station. So at this point, if you look at the information, what you can do is simply just watching the video. So which means in this last link, the impact will be only for the broadcaster, because it is like taking illegal electricity from CEB. We know that some people are taking electricity illegally, some places. So it is going to impact the CEB, not the end users. But when it comes to the attackers being here, it is going to impact the viewers because they might inject some unwanted content as well. So from these two examples, I believe you can understand, since we are using this satellite as a backbone, this is really important, right? So this is a backbone link, which means it carries a heavy amount of information. All of that information is going to get impacted, right? So that is why this security of this type of communication or the networks is really important. So as I mentioned, so there has been certain security failures in satellite networks in the history. So I tried to capture these things. These are actually not from Sri Lanka, but there have been some instances, 1 or 2 instances where there has been cases even for the Sri Lankan satellite network, right? But when it comes to like the history, if we go back to the history in 1998, there was this signal spoofing. That means somebody is trying to capture the information which is related to military. It is really critical, right? So maybe when you are sending some GPS or location-based information through the satellite link, if some opponent can get the information, they can even attack, maybe if it is related to a ship, they can attack that ship. So it is really a threat to the military operation. It was actually a threat in 1998. And on the other side, in 2007, when it comes to the satellite phones, like when we have the voice communication through the satellite links, there were some people who were able to track the private calls of individual customers. So in that case, the customer's privacy was violated, right? And in 2011, in Intelsat, they hacked, and some very sensitive information of the customers were captured from this, right? And in 2012, they hacked certain modems. So even nowadays, I believe even in our country, this can be done as long as you know somebody's username, password, and IPs and other encryption details. It is possible to get the data that they have. So those kind of modem-based hacking was happened in 2012. So this is, I could say, even though it is not going to have a worldwide impact or some large impact, it is happening even now, right? And in 2013 also, this is rather than a security failure, this is actually due to, there was a global outage due to which some voice and data services got disrupted, due to which some issues were there raised in some military networks, right? And in 2015, there was a cyber attack in this network where the whole Europe was under attack, which was a cyber attack for the malware attack, right? So in that case, like so many, I could say not thousands, maybe millions of customers were impacted. It was actually network, a satellite-based network, which was throughout the Europe, right? So which means there was a lot of people in that area. And in 2016, a set of people were able to, as I mentioned earlier, related to the TV. So they were able to hijack the uplink of the TV broadcaster and broadcast unauthorized content. So the people or the viewers were getting some videos, or in their TVs, some unauthorized content was played. So that was not actually controllable by the operator or the broadcaster at that time, because it was a sudden attack, right? And then there was the SATCOM jamming incident as well. So I believe you have heard the word jamming, which means in case that we want to prevent somebody to make communication with someone using a particular available link, it is possible for us to send an interfering signal to that particular network so that nobody will be able to make calls, right? So even now here in Sri Lanka, these jamming concepts are used around the prison, mainly the Valikada prison, where we know that sometimes it says that the prisoners have mobile phones and all these things, but the operators have deployed some base stations and they are sending jamming signals so that within that area, it is not possible to make calls. And in 2020, very recently, the Starlink also had certain security concerns. So it was actually like unauthorized access to the terminals and their architecture, right? So even the network architecture is really important. So those kind of information were captured. And very recently, this is also when it comes, it is not a direct network related attack, but for the supply chain. So we know that these satellites are manufactured using very high precision sensors and all these other electronics. So if somebody is not providing certain proper devices, it is going to have malfunction. And if the encryption is not working, maybe encryption option is there, but it is not happening properly. So it is at risk. So this is actually something that was identified in 2022. So the next thing, so I believe now from the examples I highlighted, you can understand that what sort of impact that can happen. Like if you are a satellite provider, because generally a satellite network is maintained separately as a service provider, which will provide the service of maybe voice calls, internet browsing for the operators, or else maybe navigation services, those kind of things. So the satellite networks are sort of a backbone networks which are maintained by some other people, right? So the satellite network should not be always owned by the service provider or the operator. It can be an independent party. So given that it is an independent party, there are a lot of challenges that the satellite networks have. So I have listed here one, and the main challenge why we have these security challenges in satellite networks, and on the other side, the other minor challenges. So if we consider, I believe as soon as you see this word multiple access, I believe all of, or at least many of you would know what do we mean by this multiple access. So what do we mean by multiple access means? Now, as I mentioned, if a particular operator wants to have IDD calls, they will go to a satellite operator or a service provider and would say that I want to have a link so that I can forward my calls from Sri Lanka to USA, right? And also on the other side, maybe some broadcaster would come and say that I would like to host my TV channel, maybe from here to India. So which means different users, different terminals, different applications will share the same satellite or the transponder or the same backbone link. So when you have multiple applications, which means like when it comes to TV broadcasting, when it comes to other, let's say mobile operators, it is always a risk. So maybe some people can do eavesdropping, right? So I believe maybe you would have heard this eavesdropping means somebody is trying to listen to others' information, right? And also interference. So somebody can maybe intentionally or unintentionally interfere because they are transmitting certain frequencies. And on the other side, there is this concept called the spoofing, which means that some fake users are trying to show that they are like real users, but they just generate some ad hoc traffic, which is not actually the required legitimate traffic, right? And also the consumption of the bandwidth, right? So since many of the people are consuming the bandwidth, this is going to be a problem. right? So when we are managing these satellite networks, this multiple access based challenge that we have is something that we cannot omit, right? And other than that, these are the other key reasons for which the security challenges can come. So because the broadcast nature, right? So on like if we take the TV broadcasting and others, since this is not guided, right? So I believe when it comes to channels or the transmission media, we have something called the guided transmission medium and unguided transmission medium. So when it comes to unguided transmission, it is like broadcasting, right? So anybody who has the intelligence of decoding the message will be able to capture, right? And also the other challenge is the long distance and also the latency. So that means the link, since the link is very large distance, there is time for somebody to eavesdrop or else to attack or else to capture the information, right? And also based on the mobility, as we said, that the Earth is moving, the satellites are moving because of this dynamic topology also. There are certain challenges so that somebody unintended might get signals, right? And also the limited terminal security. So when it comes to a lot of secured hardware, right, they might be very costly. So some service providers of satellite networks might go for low-cost components, which is a security challenge, right? And of course, jamming and denial of service. That means, as I mentioned earlier as well, some people or rather an attacker who knows about the network can jam signals so that we will not be able to send information. So these kind of jamming experience can be there when it comes to like if you have a war, the military related things, this is always a risk, right? And also the malware and software attacks, because we are using different, like when it comes to the networks, we are using different hardwares which have certain software, and maybe we have certain very frequently used softwares as well, which can be targeted by others, right? And also, as I mentioned earlier as well, the third party as well as the supply chain, the people who are providing the components to these networks, they might not exactly understand how much these services are critical, so leading to poor quality components. And on the other side, the security will be threatened, right? And the other thing is if we do not have encryption. So this is something I believe outdated, right? So today you will not be able to see any single network without encryption, even in our mobile phone, right? So maybe we do not experience it personally, but when we are sending our voice signals, when we are sending any transactions, let's say I'm doing online banking, for all these things, encryption is there, right? So this is, I believe now it is not quite a challenge unless otherwise you come up with a customized network, right? So from this, I believe you can see what are the different areas due to which these security challenges can appear, right? So in that case, it is really important, really important for us to identify whether my communication is secure, because we are ultimately sending information, especially when it comes to satellite network, we are sending other networks information, right? So maybe TV broadcasters will be sending, and maybe some telecom operators will be sending information. So the satellite network is very much important. But equally, as I mentioned, the end user links, as even in communication networks, from the access network to the core network to this link, everything should be secure, right? So now with the word security, the next thing that we need to understand would be the encryption, right? So what exactly we mean by encryption, right? So encryption is a process that we use to convert our direct information into an unreadable format using some techniques, right? So as I have very briefly shown here, the sender. So this plain text is like the bits that we send, right? So let's say in case of voice communication or even data transmission, we know that we send information nowadays using IP packets. So if we look at an IP packet using an IP or the packet tracer, right? So we can get what is the information going, right? So which means if it is plain text, it is easy for an attacker to get the information. So that is why we do encryption. So from the sender side, it is required for us to do encryption. So for that encryption, we use algorithms or the techniques, which we will discuss in the next few slides. And once encrypted, we call it as a cipher text, which means just looking at it, we cannot say what is this word, right? So let's say I typed in WhatsApp, hello, and I just sent it to one of my friends. So if I have done the encryption, or if my network has enabled the proper encryption end to end, then at the middle, if somebody gets this, they might not be able to identify what is the message, right? Unless otherwise, on the other side, you have the corresponding key and you know what is the algorithm that is being used, right? So the decryption happens on the receiver side so that they will get the readable information, right? So why this encryption is important? I believe from the previous few slides that I discussed, this is already proven that why it is important. The first thing is confidentiality, right? So as I mentioned, if somebody is making a call, we do not want somebody to keep listening, tapping our call, and maybe we are just, let's say in a data session, we are just logging into our online bank account. So we do not want others to get to know my username and password because they can do the transactions there, right? So that means confidentiality, right? So even in a telecom network, one of the key requirements is to maintain the confidentiality of the user. So it is the same here when it comes to satellite networks as well, right? And integrity, right? So which means we are sure that the information that we send are not being captured or changed, right? Because now when we do the encryption, what happens is unless otherwise the service provider deliberately check on it and do the decoding, even they cannot see it. So the integrity is there, and also we can authenticate, right? So we are authenticated to send the information, right? So everybody cannot send information, only the authenticated people who have the encryption key can send the information, right? So that is also why. And also compliance and trust. So there are different compliance requirements in standard operating procedures, right? So whenever we are having a mobile network or when we are having satellite networks, it says that we need to have a standardized technology, right? So if we think about these different communication, I hope you know that it is the ITU, International Telecommunication Union, which is actually coming up with the different standards. Even for the satellite communication, this is the frequency, this is the uplink data rate, this is the modulation technique. All these things are defined by the TRC. So they have given certain compliance requirements. They have said that in this technology, you have to use this encryption. So it is not up to an operator and say, no, we do not need to do the encryption. No, they have to comply, right? And also, especially for, as I mentioned, for the satellite communication, this is very, very, very critical, right? Because it protects the data, which is of a vast range of fields, right? So now if we take like a mobile operator, if somebody is get into that network, it is going to impact to that users. Yes, it is a huge portion, but it is only to that network. But if we take a satellite link, as I mentioned earlier, there will be different services maybe the satellite, or not satellite, maybe the navigation services, maybe the weather data, maybe, and then the voice data. All these are going inside the satellite communications, right? So in that case, satellite link, the encryption in satellite link are mandatory, right? So it is, I'm not telling that it is not mandatory for broadcasting. It is mandatory for them as well, because according to the compliance, they have to, or the standard, they have to do it. But what I'm telling here is impact. How many customers, how many people are going to get impacted because these satellite links are going to carry very high information, right? So in that case, encryption is really important. So I just included this slide for you to understand where we do the encryption and decryption, right? So in the previous slide also, when I was discussing about the TV broadcasting, I said that when we have the information, so when we take this satellite station, the analog signal is generally converted nowadays to digital using analog to digital conversion. And then if we need to compress, and then if we need to do channel encoding, all these things will be done. And the final step that we do before transmitting is the modulation. So when I say modulation, I believe many of you might know, but in case if there are any of you who do not know, so maybe if we take a particular signal, this happens mainly when we are talking about the wireless communication. So in order for our signal to be transmitted through the wireless antenna, wireless channel, we have to use an antenna, right? So in this satellite, the transponder, we have the transmitter, we have the receiver, right? So at this transmission, we have the antenna, right? So in our mobile phone, we have the antenna. So this antenna, the size of the antenna depends on the frequency that we generate, right? So according to the antenna theory, maybe you would have learned that generally the length of the antenna should be half of the wavelength, right? So lambda divided by 2. So if we are to transmit a signal with very less frequency, we will need antennas of few kilometers, right? So we cannot manufacture antennas of few kilometers. So in that case, we have to make the frequency high, which is done by modulation. And in addition to that, in satellite, we have to do up conversion anyway, because we are transmitting it through a longer distance, right? So in that case, we have to further up conversion. But in whatever the communication system, we do this modulation. That means we make the signal capable or possible to be transmitted through the antenna. So prior to this arrangement of modulation, we can do the encryption, right? So this is in the pipeline of this way, right? So which means we are doing all the other compression, do the channel encoding, and finally, because even the channel coding information is our own data. So all of those should be encrypted. So that is why just prior to the transmission, we do the encryption, right? And on the other side, we will have on the downlink, we need to, at the receiver, it will be receiving, and then it will do the amplification using the low noise amplifiers and down conversion. We'll do the demodulation, which is the opposite of this. That means afterwards, we have to do the decryption. Right, so these are the 2 points that we have to do the encryption and the decryption in the RF signal processing part, right? And once we have done the decryption, then we can do whatever the other signal-based processing that we have done, right? So I believe now it is very clear why do we need encryption and where we need to do the encryption in our communication link. Right, so now coming into a little bit of complex content, but I will try my best not to make it complex, but just for you to have an understanding. So don't worry that this slide includes a lot of details, but I haven't kept them all so that maybe you can refer to it later and then just do a little bit of research and study on them. But what I just wanted to highlight here is when it comes to encryption techniques, there are two types of encryption techniques. One is said to be the symmetric encryption, and the other one is asymmetric encryption. So this encryption, as I mentioned, these techniques are not only specific for satellite networks, right? So whatever we are discussing here is not only for satellite networks, but it is applicable even for the mobile networks, the TV broadcasting, the radio broadcasting, the radar communication. For all these encryption techniques are there. But the suitability of different techniques will depend on the level of security that we want and the easiness of attacking the information that we send, right? So in that case, when it comes to satellite networks, we will need a very high level of security. So which means we need to have very precise encryption and decryption techniques, right? So the encryption techniques we have can be classified into two types that you can see here, the symmetric and the asymmetric. So what do we mean by symmetric encryption is, so at the transmitter side, the key that you are using. So we have a certain algorithm how to do the encryption. And when we are doing that encryption using that algorithm, we have to insert a key, right? So that key is something private within this end two users, right? So this key is really important. So in the symmetric encryption, the feature is that the secret key is the same for the transmitter or the sender and the receiver as well, right? So for the sender as well as the receiver, the key is the same, right? And when you think about the asymmetric encryption, as it is shown here, the sender side key is different. That is why it is shown in green color and red color on this side. The keys are two different keys. So now you might wonder, when we are opening a door, if we have two types of keys, how can we open the same door, right? So your question is valid. So if we think about, that is why I just had this very layman example for you to understand, right? So in this case, it is like the information that we want to send, we are putting into a very secured box and sending, so that at the receiver side, once the box is open, it can be seen. So in this symmetric encryption, the key that we use to lock as well as open is the same. That means we have just one key hole, right? Whereas if you look at this, the asymmetric encryption, right? So here you can see that there are two, right? So you can see there are two keyholes, right? So the key that the sender is using is only to open the box and put things and lock it and send. Whereas the recipient or the receiver is going to take the message from a different keyhole, to which only the receiver has access to, right? So even the sender does not know what is this key. Only the receiver knows. So from these two mechanisms, I believe you can understand that we could achieve a more level of security in asymmetric encryption, right? So maybe this concept might be a little bit difficult to understand, but I think with this example, it is easy for you to understand. And when we talk about the different techniques, it will be easy for you to understand it further, right? So when it comes to, once again, I'm repeating. So when we take the symmetric encryption, the sender and the receiver both use the same key to lock and unlock the message that we send. Whereas in the asymmetric encryption, there is a key that if somebody gets, can open and send information, but once it is sent, only the receiver can open the box, so that only the receiver will see the message, right? So under these two classifications, right, so there are many other encryption techniques as well, but here today I just thought that I will be discussing these four, from which the first two, right, so the advanced encryption standard and the data encryption standard are symmetric key algorithms, right? And out of these two also, this is the most oldest method, right? So it was actually deployed in earlier networks, but later it got evolved into advanced encryption standard, AES. Whereas the two that you can see on the right-hand side are asymmetric key algorithm. So when it comes to even though I explained the symmetric and asymmetric in terms of the mailbox, so when it comes to the technical terms, the real difference between these two is like these use the same key, which is sent or generated by the sender, right? So the sender is generating the key and he's sending to the receiver. This is the key that you have to use to decode the message. It will be sent in a different message. And then once the encryption is done, the receiver will know, okay, this information that he or she is getting needs to be decrypted using this key that was sent earlier by the sender, right? Whereas when it comes to these two techniques, the reverse Shamir-Adleman, so this is a combination of a group of people who came up with this method, and this elliptic curve cryptography, which is ECC. These two are mainly working on mathematical methods, right? But only important thing is in these two cases, they have two keys. One is said to be the public key and the other one is the private key. This private key is only known to the receiver. It is a key generated by the receiver himself, which is not even shared with the sender, right? And another difference in these two techniques is that, as I mentioned earlier, in symmetric key algorithm, the sender is the one who is generating the key. But when it comes to the asymmetric key algorithms, in both of these cases, it is the receiver who generates both the public key and the private key, and receiver sends only the public key to the sender, right? So which means the private key is only known to the receiver. So which means it is generally secure, right? So before moving on to this, if I just try to explain it in this way also, because I would prefer it drawing here, right? So if you take the symmetric, so I will word them as sender and receiver, maybe not the satellite and the ground station, because we can have the sender and the receiver, anyone, right? So when it is symmetric, the key is generated at the sender side, and first the key is sent, right? So the key is sent to the receiver, and then separately the encrypted information using this key will be sent, right? So information will be sent. And on the other side, in the asymmetric method, right? So in the asymmetric method, here, let's say we have this sender, and here we have the receiver. So sender will say that I need to send some information to you, right? And the sender will actually send another key to encrypt the public key that the receiver is sending to this side, right? So there is more security than symmetric in that manner as well, because sender is going to generate either AES or the DES based encryption, and will tell the receiver, when you are sending the public key, send it using this encryption. So even the public key is shared using a encryption method, but here the key is sent with certain security only, right? So now on the asymmetric encryption, what the receiver will do, he will generate public key and the private key, right? And this public key will be encrypted using this AES key that the sender sent, and public key will be sent, right? So which means the sender is now having the information. So using the public key, the sender will send the information, or rather encrypted information, right? So here also the encrypted information. So here public key is also sent in encrypted manner, right? So the encrypted information is received, but the speciality here is the receiver is not going to use the public key to do the decryption, but it is the private key that he is using to decrypt. Right, so that is the specialty, because even when somebody, when let's say a receiver was sending this public key to the sender, if somebody identified it and tried to send on the other side, the things that are coming on this way, the attacker cannot decode or decrypt. Why? Because to decrypt, this private key should be there. So the information is arranged according to this manner, right? So now if we look at the asymmetric, first we will look at the symmetric method, right? So in the symmetric method, I will first take the AES, Advanced Encryption Standard, right? So in this case, generally, when it comes to weather satellite data encryption, this is an example using that. So generally for weather satellite data encryption and decryption, this method was used, or rather even now it is used, right? So the information is converted into binary, right? So we know that whatever the images, we cannot directly send as images, we have to convert it always into bits. So once it is converted into bits, right? And then it is being converted into the hexa, right? So hexadecimal, and each byte, right? So each byte is being XOR. I believe you know what is XOR when it comes to the different operations that we do. I believe you know that we have AND operation, the binary operations, and or not nor. Likewise, we have XOR. So it is the XOR operation that we do here, so that we are getting some information that cannot be actually readable, right? So this now we cannot exactly readable because we are using the initial key, right? So in this symmetric method also, it is not just one key, it is a group of keys that are being generated, but that total group of keys are sent to the other side, right? And it is the sender who is generating the key. So out of the keys generated, the first initial key is being used to make this XOR. So it is like XOR operation that we do. And then there is this actual encryption that we do, and it is done for multiple rounds, right? So in this case, in example, it says that we are taking 128 bits. We are doing taking 128 bits and we are encrypting. And this from A to D, these 4 steps go 10 times, 10 rounds, right? So just to increase or the randomness, right? So what exactly we do is we are just mixing the information so that when somebody receives, they cannot get a meaning. So that is done 10 rounds from A to D. These 4 steps are done 10 rounds, right? So here first what we do is, that is, we call it as sub-byte. So byte by byte is replaced by something called the SBox substitution table. So there is a separate table. This is just to confuse the person who are attacking, right? So there is no proper, like, why exactly we do, just to confuse the person who is reading trying to read the information. So the 8 byte, the 8 meaningful information that we had is now replaced by something which does not give you any meaning, right? And that, so here you can see I'm showing byte by byte. So it is like a matrix that we have created here. So then what we do is we shift the rows, right? So we can shift the rows from left towards right as we want, so that it will have different offsets. So this is not going to go directly like this, but it is going to get shifted. And then we mix the columns as well. So we exchange it on the rows and we mix it as columns. And once again, once we do another XOR operation here using another key. So the transmitter or the sender and the receiver both knows what is the sequence of the keys that we are going to use. It is a set of keys that are being generated. First key used here, second key used in the first round, and then once again, when this is going in the second round, another key likewise, the keys are used. So this happens 10 times. So you can see the things or our original information gets mixed and mixed in different ways, right? So nobody can predict finally what we are going to get, right? And once it has been done, it can be sent, right? So this is what we call as the cipher text. So this is the plain text that we had. Here we have the cipher text we have. So on the receiver side, it is the total opposite that we do, inverse of whatever the things we did, right? So first we have to take it like, we know that we are getting it from binary because in the transmission medium, we do the modulation. So those parts are not shown here. So once we have done the modulation and sent, it is analog signal once again. At the receiver, it will be demodulated, which will give you back the bits. So the binary bits is then once again converted to bytes. And then we do the XOR operation, this one. And then we have to do the inverse mixing of columns. And then we have to do the inverse mixing of rows. And then we have to go back to the SBox, inverse of the XBox table mapping. And then finally, this is also once again done the 10 times, right? So here you can see this was done 10 rounds. Likewise, this is also going to be done 10 times. And then finally, this initial key, you will get your original unit, right? So from this, you can see what exactly we try to do in encryption is just to rearrange the information that we want to send in a very mixed way that any attacker will not be able to predict, right? So this is the encryption technique, the AES, Advanced Encryption Standard, which is generally we use for the weather satellite, right? So even the weather satellite data are encrypted, but these methods, as I mentioned, this is it is secured, but not much secured as the asymmetric one. So that is why even we could do some decryption and look at the weather data if we have these SDRs and all those things by connecting to the relevant frequency, we can get the information up to a certain extent, right? So in that case, this is the AES, right? And the next one is the DES. It is actually also a little bit similar to the AES, except the row and column mixing, right? So in that case, we do not do row and column mixing. But here, now earlier in the AES, we said that it is 128 bytes. But it is not always 128 bytes. There are different configurations, right? So if you want, you can have 128, 256, different rates are there. So you can decide what is the rate at which you are going to do this operation, right? So this is AES 128, which you can see here, but this can be changed as we want. So maybe in satellite, we might be using AES 128, but maybe in mobile communication, we might be using AES 512 because we need more security, right? So when it comes to the DES, which is the data encryption standard, this is actually the oldest. Actually, AES is the, we could say, the development of DES. So the first most historical method is this. And it was then improved into the AES, but I introduced AES because when it comes to the symmetric encryption techniques, the AES is the most highly recognized. This is, we could say, like now a little bit of obsolete. So that is why I included here that this is the old system, right? So even in satellite TV now we do not use it, but this is what it was used. So in this case also you will see a similar sort of steps are done, right? So in this case, instead of that S-box tabulation, we have something called the IP table, which is initial permutation table, which is once again another mapping of the different bit sequences into some other symbol so that it will, the things will get mixed, right? So it is going to, like the bits are, when we interpret the bits in a different way, the meaning will be not known to anybody, right? So in this case, we can, generally we use 64-bit blocks, right? So compared to earlier, we had 128 and upper versions, but here generally it was 64 bits. So we take the 64 bits and we do the this bit mapping, right? And this block, the IP table mapped block, is then actually divided into two halves, right? So left half and the right half, right? So that is why you can see this R, right? So here you can see when it comes to it, we have 64 bits. So the 64 bits are divided into two. You will get 32 bits left side and right side. So we will keep the left side as it is, but we will take the 32 bits of the right-hand side and we will expand it to 48 bits. So there is a mechanism that how do we expand it, right? And then what we do is we use the key, right? So in this method, this is where we use the key. And you can see here also, starting from A to D, these four are done, sorry, up to E, all these are done 16 rounds, right? So earlier we said in AES, we are doing 10 times, right? Here it was 16 times. So what we do 16 times is first is taking the 32 bits and expand it to 48 bits. And the 48 bits is then XORed. So the same operation is done as in AES with the secret key, right? And then we use the S-box tabulation once again to map. And then we get the final permuted output. And then what we do is now we have the left-hand side and the right-hand side. So we swap the left and right, right? And this is being done 16 times. And once it is done, we once again do a permutation, and then we get the final bit sequence to be sent, right? And on the decryption side, what we do, so the decryption, it is starting from here. So we are taking 64 bits each. So the same thing, the opposite side will happen, right? So we will have to take the this permutation, inverse permutation will be done. And then we have to do the 16 rounds in the reverse order. This was done from A to E. Now we do from E to A, right? So we have to swap once again the half and then the permutation. And then we will have to do the S-box inverse mapping and then XOR and then reducing from 48 to 32, so that we will be getting the 32, and the other one will be then swapped, right? So from this also you can see, only if we have this same key, it is possible for us to send and receive, or the encryption and the decryption can be done in this manner. So anybody who is able to get in touch with the encryption key can engage in doing either encryption of any information to be sent and broadcast, or else any information coming can be decrypted, right? So in that case, this is how these two works. And the third one, this is the RSA, which is the name is a little bit, even I do not keep reminding it. It is reversed Shamir-Adleman RSA. So it is asymmetric. So as I mentioned earlier, in this method, we are not going to use the same key, but you can see here, I will explain this by drawing it in a separate document, because this will make a little bit complex, because we have to first share the key and then only we do the encryption. So in that case, I will discuss the steps in a different document, right? But from here, you can see that this is more mathematical, right? So you can see your ciphered text is created from the message. This C means the ciphered message. The message M means your original message is made to a certain power, and then it is being divided by N. Mod N means we divide and take the remainder, right? So it is a mathematical operation that we do. And on the other side, you can see here we are figuring out at the receiver the message from the ciphered message. Here we define the ciphered message from the original message using this, and this is ciphered message is being converted to the original message, right? So I will just go to this so that it is easy for me to explain, right? So if we think about this, what you call this RSA method, right? As I mentioned, it is the sender who generates the keys, right? So sender generates the public key as well as the private key, right? So it is the sender who is generating. So first step is generating the public key and private key by the sender. Then the sender will send this public key using the AES encryption to, I made a mistake. It is not the sender. Yeah, it should be receiver, right? Sorry, I made a mistake. This is receiver, right? So it is the receiver who generates. In this case, you can see in symmetric, it was the sender, but in asymmetric, it is the receiver who is generating the private key and the public key, right? So sorry, I made a small mistake. So the correction, the RSA, it is generated by the receiver. So receiver generates the public key and the private key, and he only sends the public key. So the sender knows the public key. Sender takes the message to be sent, use the public key, do the encryption, and send it to the receiver, right? So in this case, if I just explain the steps that we do, so first, the receiver, the first step is generating, right? So in this case, before moving on to the encryption, we have few steps in generating keys by the receiver, right? So the first the receiver will do is he will check, or he will generate 2 random prime numbers, right? So he will generate 2 random prime numbers. So let's say the 2 numbers are P and Q, right? So he has 2 numbers. So from this, he will calculate a value N, which is P multiplied by Q, right? And then he is going to calculate something called the Euler's quotient, right? So there is something called the Euler's quotient, which is simply the multiplication between P minus 1 into Q minus 1. So these are numbers, right? So prime numbers, I believe you know what are prime numbers. So 7, 11, 2, 3, those are prime numbers. So you can get P to be 7, maybe Q to be 11 likewise, and then you can try this thing and see whether you can get it. So your N will be the multiplication between these two, and this phi N will be P minus 1, in this case 6 and 10. 6 multiplied by 10, it will be 60, right? And then the receiver will select the public key which he needs to send to the sender to be E and N. This is a combination, two numbers. N is this N, but what is E? So he has to select a random E value between 1 and this quotient, right? So this E is once again a random number, but between these two values, and N is simply the multiplication between these two, right? And then this is, when this is selected, it is required to get the greatest common divisor, right? So we have something called the greatest common divisor. I believe when we were doing maths in O levels, we know this greatest common divisor. Out of this E value that we select and the phi N, these two to be 1. That means it is once again co-prime numbers, right? So they do not have any other factor than 1, which is common, right? So the receiver is selecting the public key having E based on this condition and this N coming from this. So this is the public key. So this public key is sent to the sender, right? And what is the private key? There is a private key which should also be generated, right? So this private key is said to be D, right? So this D is multiplied when we, how we select this D is when we multiply this D by this value E we selected, it should be equal to 1 mod of this value, right? So if we take this quotient was in the early example, this was 6, this was 10, so 6 into 10. So that means 1 mod 10. So 1, when we divide it by 60, the mod will be once again 60. So the multiplication between D and E should be 60. So likewise, the private key will be selected in this manner and public key is this manner, right? So now what the receiver will do, this public key will be sent to the sender. So now the sender has the public key. So what the sender will do is sender is going to generate the cipher text message as M to the power of E mod N, right? So M means the message. You take the message. So message is converted to a number, right? So we know that if we have hexadecimal or bits, we can convert it into decimal numbers. So that number to the power of this E. So let's say if E is 2, 20 to the power of 2, right? So then we take the mod of that in terms of this N, because we know that N is also here. N is also known. E is also known in the public key. These two are the information sent. So the sender sends the ciphered message. So on the other side, how will the receiver detect this, right? So the receiver is going to detect the message M such that this is C to the power of D mod n, right? But the important thing is in this according to the mathematics, right? So if you just go through this mathematically, you will see that this, when we have defined the things according to the rules that I told earlier, these two comes true in this way, right? But the thing is now why we say that this communication is safe, secured, because to decode this M, we need this D. What is this D? It is private key D, which is only known to the receiver. So even if this ciphered message is now received by some attacker, if they do not know this D, they cannot generate the message. Because this D is only known to the receiver, not even the sender. We do not send it in the transmission media. It is only saved in the receiver's device. So which means this is very much secure, right? So that is why this method is said to be, RSA method is said to be more secured. We have a very mathematical way of generating it, and we are 100% sure that this is going to work and nobody can look at the information, right? So that is the exact thing that is shown here. Do not worry if you did not get all the steps, but what you need to understand is that according to this mathematical, right? So what I just wanted to highlight here showing these steps is, this is totally a mathematical method, right? Totally a mathematical method which we can recover if we know D. But the trick here is this D is not known to anybody else except the receiver. So in that sense, this is very much secure, right? And then if we think about the last one, this is said to be the ECC, right? So it is the elliptic curve. So which means, as you can see here, we are using this sort of an elliptic equation, right? So the same way that we had earlier, right? So I will maybe, this is a little bit, this is a little bit more, I could say, complex, but if you are really interested, you can, I believe, now understand even if you look at the different steps, right? So here, once again, what happens is, once again, the private key and the public key is generated. But the private key and the public key is generated not simply by, let's say earlier in this case, it was just the prime numbers P and Q, just guess numbers, right? But here in the receiver, what it does is it takes an elliptic curve. So if you look at what is an elliptic curve, it is like an equation y squared equals x to the power of 3 plus ax plus b. So it is like an elliptic shape curve. And in that elliptic curve shape, we are taking a base point, right? So we are taking a base point, which is shared with the sender, right? So receiver generates this, but he shares it along with some other information. So based on that, once again, as we said earlier, the public key will be different, right? So here you can see the public key in this case is Q, right? So the public key is sent and the private key is DC, right? So in that case, different public key and different private key is there once again. So compared to the previous method, the difference here is the keys are generated using this elliptic curve, right? So as I mentioned, elliptic curve is like if we take an equation, right? Right, so elliptic means elliptic curve. So it is like when you have y to the power of 3. 2 is equal to x to the power of 3 plus ax plus b. Some curve like this. So you can have different a, b values here. So it is up to the receiver to decide what is the elliptic curve. And in that elliptic curve, as it is shown here, we take a particular point. So that point, along with this elliptic curve information, is being sent to the sender so that it is possible for the sender to encrypt using that information. So when the sender is encrypting, sender is generating two encrypted cipher texts, C1, C2. Two cipher texts are created, not just one, but two cipher texts are created, and those are sent. So somebody who gets those two cipher texts, if they do not know the D values here, the D value is only with the received party, right? So only the receiver knows, because he generates the public key and the private key, and he sends to the sender only the public key. So private key is only known once again to the receiver. So in that case, only the receiver will be able to decode. So the steps are not equivalent, but the methods are the same. And this is said to be more stronger even than the RSA, right? So this is generally considered now, even if we take the satellites we have nowadays, in emerging satellites, we will be using a lot. You will be seeing that we will be using this ECC more, because guessing the private key is not easy even as much as RSA, because here it is totally different, right? So in that case, I will not go through the exact steps for this, but I believe with the explanation with the RSA, you can understand only the way, as I mentioned here. In RSA, we started with generating a random P and Q prime numbers. But here, we are not just randomly generating prime numbers. Here, we are taking a curve, and on the curve, we are taking a random point. And that point value is what we use to proceed further, right? Based on that value, we are generating the public key and the private key, and the public key is sent to the sender, so that sender will be encrypting. And on the receiver side, once again, it is not the public key used, it is the private key that is being used. So unless otherwise somebody do not have the private key, the message will not be able to be decoded, right? And then I have just included another 2 slides just to explain the usage of these different encryption techniques in different layers, right? Because we know that even when it comes to satellite communication, we will be transmitting most of our information as IP packets. So we will have the layered architecture, right? And if we look at these different encryption techniques, we will be using these different techniques in different layers, right? So here you can see in this third column I have mentioned. So when it comes to AES and the DES, those are lower layer encryption techniques, right? So the data link and the network layer, layer 2 and 3. But when it comes to the RSA and the ECC, you can see application and presentation. So it is like 6 and 7, very high layer encryption technique, right? So these are more stable and more secure, right? Also, I have given certain users where we use these specific techniques. As I mentioned, this CubeSat, in those kind of applications, this is used, and for IoT. And ECC is basically, I could say, the encryption technique that is being very much trending a lot, because it is more secure. So I have just summarized all these things that we have discussed here, just to indicate what are widely used and what are not really used in satellite networks, right? This is only for the satellite network specifically, because when it comes to some other networks, like let's say TV broadcasting, or else let's say for a mobile network operator, This might change depending on the level of security that we want, right? Because when we consider to do this encryption, decryption, it takes certain resources, it takes certain power. So depending on those aspects also, we have to think which encryption techniques suits which application, right? But as you can see in this last line, so you can see I have compared them using the strength. So we can see that this AES and this ECC is also very high, right? And when it comes to performance, this is generally very fast because we can simply send the secret key. But here we have to have a small generation mechanism and then to do the encryption, right? And the power consumption, this is very much low. And in satellites, these are used in different satellites. But as I said, this DES more or less obsolete as of now, right? And as of now, widely used, this is, as I mentioned, it is getting increased. And this is already are there in many of the existing satellite networks, right? And RSA is also a certain applications we can use, right? Yeah, so with respect to the security, those were the aspects that I wanted to discuss. Mainly, I just wanted to highlight why we need security and level of security that we need for different applications. All are not the same, and then different techniques. But security is one aspect when it comes to the challenges that we have in satellite networks. So here, what I wanted to just highlight is what can be the other challenges. So if you take, like, if you are interested, like this encryption techniques is also a research area. Like now, as you can see, this RSA and ECC, those are mathematical techniques, right? So likewise, maybe some of you, if you think you can see, okay, if we do this, maybe this cannot be decoded. So likewise, that mechanism, right? So coming up with those new mechanisms is a research area that you might be very much interested in. But other than that, when it comes to practical satellite networks, these are the challenges, especially when it comes to like integrating or using satellite for the backbone for communication. I could say like for mobile communication or telecommunication industry, the latency, right? Why? Because you know that when it comes to the 5G and 6G networks, in 5G, under the different use cases, we know that URLLC is one technique, right? So ultra reliable low latency. So we need to have low latency in our communication network, especially when it comes to applications like remote surgeries, right? Where the surgeon is maybe located somewhere in USA and the patient who gets operated will be here in Sri Lanka. So the commands that the surgeon gives to the robotic arms should be received less than 1 millisecond. So this latency in the satellite networks is a challenge for us to integrate satellite into 5G, 6G networks, right? And also when it comes to the bandwidth, right? So we know that radio frequency is anyway limited compared to visible light, right? So in visible light, we have a vast range, but the range in which our satellite networks operate, it is limited. So the data rates depend on the bandwidth that we have. So the capacity is limited. So that is also one area that you can work on, like how to reduce the latency, how to increase the bandwidth efficiency, and also the weather impact. So we know that when there are clouds, when there is rain, this link is not going to be stable. So how we make it reliable, right? And also, as I mentioned earlier, we need to have handovers, providing coverage as well as handovers. So this is also another important aspect, and also the costs, right? Because I believe one of the main reason that maybe many countries do not have these satellite networks, including Sri Lanka, is the cost. So compared to the cost that we have to bear for the fiber networks, yes, the initial cost is very high, to lay the cables under the seabed. But once it is done, it will be there for a longer time. The maintenance might be, maintenance is comparatively less, right? But when it comes to the satellite networks, we have to always maintain the ground stations. We have to look for the transponder operation. All those things are there. So the cost and the complexity is also a problem. So it is also can be researched how we can reduce cost, what sort of things that we can do. So these are few challenges, and we need to overcome those challenges for these future directions, right? So here I have listed future directions, including this integration with 5G and 6G, right? So as I already explained, it can, like, I believe you can understand that integrating the backbone of our telecom networks into satellite networks is a challenge if you want to have less than 1 millisecond latency for applications, right? But this is a future direction, right? So if you can come up with a way of developing these things, it is possible for us to integrate it with 5G, 6G, and also in IoT applications, as I have given here, and other advanced technologies like for AI-related applications, right? And also to provide global connectivity. So we know that even the Starlink says that they can even reach out all the rural areas. So that is also a certain aspect. So future direction is there, because when it comes to, like, let's say we are going to deploy a tower in a very rural area, maybe we do not experience it because Sri Lanka is a small country. But in other large countries like China and USA, we might know that the geographical area is large. Maybe they have a large, what you call forest area. So how can we deploy sites inside forests? Rather, it is easy for us to go for satellite. So likewise, there are good things, a lot of good things based on which we can develop the satellite networks for the use of this trending fields, different trending fields, like as I showed, like telecommunication, and also the TV broadcasting, the navigation, the weather, the military, right? So the military and other navigation things, all these things are possible if we can improve these things further, right? So I believe in SEDS, what all of you are trying to do is sort of this, I believe. So I believe with this information that I gave, there are certain areas that you can think, even as projects that you can try out to develop this to be integrated with the other applications more. Yeah, so that's all which I just wanted to discuss with you today. So I believe I was able to share with you certain valuable information for you to capture certain things. So I believe if you have, this is the time for our Q&A session. So if you have any questions, you can ask. So over to the moderator.
Thank you so much, Ms. Dilanka, for that fascinating and insightful presentation. I know our audience has learned a great deal. Now it is time for your questions. If you have any questions for Ms. Dilanka, you can scan the QR code on the screen to use Slido, or simply drop your question in the Zoom chat box. We will answer as many as we can. I believe we have one question. Do you think that LEO satellite internet constellations like Starlink will replace mobile cellular networks in the future?
Yeah, so I think this is a very interesting area. I believe even like when it comes to the operators that who are working in this field are thinking of. But what I believe personally is that the mobile cellular networks might not be fully replaceable, because when it comes to the satellite communication, I believe one of the key challenges, another challenge that is there is like providing indoor coverage, right? So even when it comes to like GPS locations, you know that when we are inside the buildings, we might not have coverage, right? So we do not get the GPS tracking. So which means there are certain limitations that the satellite connections can go. So in that case, I believe it is not going to replace fully, but they are going to complement, obviously, right? So it is going to complement, as I mentioned, maybe there can be certain, so when it comes to the satellite connections through internet, if we cannot do the in-building, mobile operators should be there. Whereas in areas like very rural areas or very, if we take maybe in the ocean, the mobile operators cannot provide coverage. So in that case, yes, the Starlink sort of operators can provide. So those are going to be complementary. Both will exist.
I think there's another question, Ms. Dilanka. Are the satellite communication systems also monitored by the ITU?
Yes. So when it comes to the ITU and the regulatory bodies in Sri Lanka, if we take for Sri Lanka, we have TRCSL. So whatever the frequency that we transmit, if any apparatus is transmitting a licensed frequency, it is monitored. Right. So in that case, yes, satellite, whatever, if you go and just look in the frequency spectrum allocations, you can see even in the TRC website they have, and also in the ITU website they have the allocations. It is the ITU who say that develop the standard and say it is the 4 gigahertz, it is the 10 gigahertz that is going to be used. Anything that somebody is going to use for transmitting a frequency is monitored by the ITU and the regulatory bodies.
Thank you, Ms. Dilanka. I think there's one last question. Can companies like WhatsApp or Apple end-to-end encrypted messages be or use unlock data in legal case? I think they're asking whether WhatsApp or Apple are able to unlock the end-to-end encrypted messages in legal cases, or is the data technically inaccessible due to encryption?
No, technically it should be accessible, right? Because when it comes to legal cases, I believe this might be arising from the scenario we also had, I believe, recently for a certain suicidal case, this Apple phone, those things were discussed. So ideally, there is a legal procedure, but we have to go ahead with the legal procedure and with the necessary approvals. The encryption can be always decrypted based on the requirement. So like even if there is a real legal requirement and the official requirement is raised to the company, they have to abide with that.
And there are some more questions. Will traditional voice networks and SMS systems become obsolete in the future due to internet-based communication systems?
Yeah, so I believe voice networks, most probably it will get obsolete, because nowadays we know that most of us will be making voice calls through WhatsApp. So in that case, and even operators would like it to get obsolete. Why? Because if you are to maintain separate voice, you have to have dedicated resources. Like I believe all of you know, I hope all of you know that when I say circuit switched and packet switched, the original voice communication is using a technique called the circuit switch. So in circuit switch technology, you have to reserve the resource for a user dedicatedly. But if it is packet switching, you do not need. So in that case, providing a voice call through circuit switch traditional networks is costly for an operator compared to data. So in that case, it is even better for the operators to have the calls offloaded. But there are challenges when it comes to the quality of service, right? So when it goes to the packet switching, it is always, we know that in data networks, we have this problem of bandwidth limitations. So in data networks, when there is high usage, we know that the packets will get dropped. So it is a problem when it comes to voice communication. But if the required quality of service can be provided, yes, there is a chance, because I believe even in other countries, the traditional voice-based networks like 2G and 4G are 2G and 3G are no more, right? So there are certain countries who have totally removed these 2G and 3G networks. So now they are on LTE or above. So starting from LTE, it is voice over LTE, which means it is packet-based. So traditional communication will get replaced.
I think there is we have one time for one final question. Could you please explain more about how it can be expanded in expanded applications, for example, by using satellite communication modules in IoT devices?
About how it can be expanded. So the question, I believe I am a little bit not very much clear. It's a satellite. Expanded. So if you're asking about how it can be expanded is related to the satellite networks. So in satellite networks, expansion comes like, as of now, maybe end users, we might not be using direct satellite enabled devices, right? So as in Sri Lanka, I believe the experience that we would have would be like just to have this POTV, not the POTV, but the dialogue TV that we have coming from satellite. So we have the satellite dish, but other than that, we do not have. But in that case, the end devices should be capable. Like if we take the IoT, so I believe you have asked about the IoT as well. So when it comes to the IoT, also we have different sensors, different components. So as of now, what we have is only the mobile-based communication. So those devices needs to be expanded to have the communication through satellite mechanism. So in that way, it is possible for us to expand it.
Ms. Dilanka, there is one more question. Do you have
Yes.
time to do that? Okay. How can users trust that end-to-end encryption truly guarantees privacy, especially in legal cases where companies may where especially in legal cases where companies may be legally required to provide access to user data?
Yeah, so end-to-end encryption technically can be guaranteed, right? So for the privacy, technically can be guaranteed. And in case of a legal requirement, none of the operators can say that we are not in a position to give the user data, right? So let's say for a certain court case, there is a command given from the judge that the end information or the information that is being communicated should be checked. There is no way that the company can say that due to the privacy reasons we are not giving it. They are bound to give it because legal comes first, because privacy comes first when there is no legal requirements, right? So if we take like day to day, if we are making calls and if we are doing other transactions, it is not, it is actually, privacy is the first thing for an operator, right? So nobody can check our details without our knowledge, right? So for even like when there are certain customer complaints, there will be certain requirements to trace customers' calls, data, those kind of things. But for that, the customer should give the consent. But if it is legal, even customer says, no, I'm not willing to give. If there is a legal documentation given by a judge from the possible courts, the user or the operator cannot reject. They will have to give. So the guaranteeing privacy is less priority when it comes to the legal matters, right? So if the court gives the order that this person's call record should be checked for this case, due to this reason, the operator or the user cannot say, no, you cannot track it. So in that case, even the operator do not have any control. If there is any legal order, a court order is there, the operator is bound to give the information to the respective party only, right? But not others, but to the respective court, to the judge, they need to report.
I think that is the end of the questions. Those were some fantastic questions. Thank you everyone for participating. And a huge thank you to Ms. Dilanka for answering them so thoroughly. Before we move to our closing remarks, we would like to present a special token of appreciation to Ms. Dilanka De Silva. On behalf of the entire organizing committee, please accept this virtual trophy as a symbol of our deepest gratitude for your time, knowledge, and support in making this final online session such a success.
Thank you very much. And I believe this is a very good initiative, and I think you will continue to do the same. So thank you once again to all the participants.
Thank you, Ms. Dilanka. Now, as we officially wrap up our third SATvision webinar, I would like to invite our ground station manager, Damiru Dilmit, to deliver the vote of thanks. Damiru, the stage is yours.
Good evening, everyone. As we come to the end of today's session, I would like to take a moment to express our heartfelt gratitude to everyone who contributed to making this event a success. First and foremost, I would like to sincerely thank Ms. Dilanka De Silva for conducting such an insightful and engaging session on encryption and security in satellite communication systems. Your knowledge, experience, and passion truly inspired all of us today. In addition, I would like to extend my deepest gratitude to the organizing committee and our remarkable volunteers who made this webinar possible. Most importantly, I want to thank all the participants who joined us today. Your enthusiasm motivates us to continue creating opportunities like this. Thank you, everyone, and have a wonderful evening.
Thank you, Damiru. And thank you once again to our wonderful audience for joining us today. This officially concludes the final online session of the SATvision online series. Have a great rest of your day, and we look forward to seeing you at the physical workshop session. Thank you.